Hello and welcome friends in the fourth lecture of this course. In this lecture, we'll be discussing about precision and errors in various surveying measurements. In earlier lectures so far, we got acquainted with the fundamental concepts of land surveying as well as we came to know about the various techniques that can be adopted for plain surveys as well as geodetic surveys. So by this time you have got fair idea that surveying is basically nothing but taking measurements in horizontal as well as vertical measurements. That could be linear measurement, that could be angular measurement. Ultimately, we have to make use of this linear measurement or angular measurement in order to plot the features that we are interested in. So, as we are trying to collect that particular surveying measurements, it is our duty to see that these particular measurements are very precise, that are accurate, so to say, that are free of certain, say, mistakes and least possible errors. So, in this particular module, we'll be focusing our entire discussion on the errors, how they creep in, and how we can minimize their extent. So, prior to discussion of this particular, say, precision in surveying measurement, we will discuss a few of the things which will provide certain backgrounds. We just discussed about angular and linear measures and their measurement in horizontal as well as the vertical plane. But each of these particular measurement is erroneous due to some imperfect instrument that we use, limitation of the procedure that we adopt, or unknowingly even the climatic conditions may also interfere with the working conditions and hence the errors get involved. So to say, we are not always in a position to understand what is the extent of the error, and hence as error is not known to us or its true value is not known to us, the true value of the measured quantity is also never known. Whatever the refined methods that we make use of, it will be assisting us to go for obtaining the resultant refined and refined. Say for example, if you are making use of certain scale which is having 1 centimeter least count, you will be able to measure certain distance, maybe say as 21 centimeter. If you are provided with the millimeter precision, if you are provided with the millimeter least count, you may express it as 21 centimeters 2 millimeters. If you go for further micro content of that particular millimeter, you will be able to express that maybe 21 centimeters 3 millimeters plus some fraction of the millimeters. So the way you go on adopting certain refined measure, you will be going for nearer to the true value of the quantity you wish to measure. But this particular process does not have any limit. The way you go on extending the refinement, you will be reaching to the true value, but never you will be uh, at the true value as such. As this particular true value is not known, mostly we try to predict the most probable true value, and accordingly the value measured is corrected for the probable errors, and accordingly it is expressed as most probable value. As we know this particular limitation, that is our responsibility to establish the control on the probable ways through which that particular error is entering, and accordingly we should be in a position to get reasonably accurate measurement. You being civil engineer, you will be using this particular accuracy and the precision number of times while dealing with the various values that you determine as a part of survey. You have to be well aware that this particular accuracy and the precision are not interchangeable terms. Let's try to understand the meaning attached with each of these particular terms. Accuracy refers to how closely the measurement or the observation comes to measuring a true value. So, here it is, say, degree of the perfection that you will be attaining in order to reach the true value. Whereas, as you try to have certain measurement repeatedly, you will be using certain equipment proficiently, you will be following certain procedure proficiently, and these particular repeated measurements and their resultants will be in close agreement with each other. So here it tells us about the degree of the precision that you will be following in order to get the results very close to each other, not necessarily close to the true value. So the precision refers to how closely repeated measurements are with respect to the other set of observed values. The surveyor or civil engineer must be following this particular accuracy and precision while determining any surveying measurement. One more important term is discrepancy. It is nothing but the difference in two measured quantities. So here the precision is revealed by repeated measurements and by observing the discrepancies. In order to understand these particular terms, accuracy and the precision, we will go through some specific analogy. Here, let's consider certain shooting towards the bullseye. As you see here, towards the bullseye, certain shooter has made these 4 shots. Here, these shots are not close to the target hit, that is the bullseye, as well as you see, these shots are not also very close to each other. As such, the set of the observations are not accurate as well as they are not also precise. Here, as compared to this particular case, the shots are that way close to the bullseye. Hence, as they are close to the bullseye, the shots can be considered to be accurate. But as far as their existence is concerned, they are away from each other and hence they are not precise as such. As you see here, these 4 shots are very close to each other. That means here these shots are precise, but they are away from the bull's eye. Hence, these particular things are not accurate as such. Whereas, as you consider this particular 4th case, Here, all these particular four shots are very close to almost at the target bullseye, and accordingly they are very close to each other. Hence, here all these four shots are accurate as well as precise. I hope this terminology makes clear the understanding expected with accuracy and precision. There are various sources as far as surveying measurement is concerned. We can consider it to be arising out of natural sources, instrumental sources, as well as personal sources. Say, for example, if we are taking certain measurement, that measurement may be getting disturbed because of the wind, temperature, humidity, or some kind of the refraction, even the gravity as well as the magnetic field of the Earth's surface. Here, these particular things are not lying within the hands of that particular surveyor or the person who is taking the measurements. Hence, here these are said to be natural errors. Here, one more example just we can consider. Say, the scale that you use is giving the designated measurements that are engraved on that particular scale are expected to give their true sense at certain calibrated temperature. But here, if we consider the existing temperature than that particular calibrated temperature, obviously there will be some elongation as well as some contraction depending on the temperature conditions, which may not be felt to us, but actually they are affecting that particular, say, engraved dimension on that particular scale. Hence, here these are treated to be natural errors. It is quite probable that the instrument that you are using, the way we consider the scale, that itself may be having some, say, error involved because of the imperfection in its construction or its adjustment or consistent use, and hence caused wear and tear of the individual parts. As such, the errors could be treated as instrumental errors. It is quite probable that because of one's limitations in senses of sight, of touch, of hearing, the person who is working in the field may be committing certain errors. Say, for example, the person who does not have the proper eyesight may not be able to bisect the object under consideration, as well as if the person has got certain shaky hands, he may not be able to hold the starting or the terminating end of the measuring means exactly at the station under consideration. The one who has impaired hearing means if one's ear is not working properly, he may not be able to sense the particular expressions, and accordingly one may be facing this kind of personal errors. So to say, here because of the natural, instrumental as well as the personal errors, there has to be some error. Hence, this error can be expressed to be the measurement which is actually had and the true value, that is the measurement which we perceive to have. The true measurement is hence nothing but the observed value plus certain correction. This correction is always with the opposite sign of the error. Hence, these corrections can be expressed as opposite sign of all the combined errors because of natural, instrumental as well as personal errors. Even we can think of types of errors. Here, let's consider the first class. In fact, this error should not be treated as error, which is blunder or mistake. So these are kind of, say, gross errors which are occurring because of due to one's carelessness, or while handling or selecting the equipment one commits Some mistakes, because of one's limitation, one may not be able to use the proper technique, one may not be able to interpret the correct procedure, and hence there would be involvement of such blunders or mistakes. Collectively, these are treated as gross errors as such. This may be positive or that may be negative. As such, the measured dimension may be more than the actual, that is its true value, because of the positive error, or it may be less than the most probable value. So here, as we consider the blunders or the mistakes, by adopting certain standard methods, one can considerably reduce and even avoid these particular mistakes. But the small fractions are not avoidable, and that are nothing but errors. So, depending on the value and the sign of the errors in successive observation, errors could be considered under these two classes. One is cumulative, that means which goes on rising or which goes on reducing consistently with the measured value. But as sometimes the error is positive, sometimes it is negative, the net effect is compensating with each other, and hence error could be treated as compensating error as such. Here, the error which is cumulative in nature is considered to be systematic errors. Say for example, for a given set of measurements, after mistakes have been detected and eliminated from the measurement, the remaining errors are usually classified as these particular say systematic errors, or there could be some random errors that we'll be discussing in this particular heading as such. So here these systematic errors follow certain definite patterns. Thus, if certain experiment is repeated under same condition, same pattern of the errors reoccur. Say for example, if we consider that the 30 centimeter measuring means in reality, in practical, has got length of 31 centimeter. Though you are repeating it, so here the plus 1 centimeter that is bound with the measuring means will be consistently creeping in with the number of measures, the number of times the scale that you are laying down, and hence it is said to be following certain say definite patterns as such. As mistakes are eliminated, as even the systemic errors, as they follow certain rules, as they follow certain fixed pattern, hence by applying certain law are corrected, the remaining surveying measurement is associated with random error only. This error is very small and equally liable to be positive as well as the negative, thus it is partly compensating in nature. Here, these random errors are because of combination of that particular sources, the way we discussed in the previous slide, that could be combination of natural, personal as well as instrumental, and even that could be cumulative or compensating simultaneously. Hence, here these particular random errors are unpredictable in nature and they cannot be evaluated and quantified exactly. As they are random in nature, they follow law of probability, and hence there is a need of applying the concepts of the probability in order to minimize these particular accidental errors. In general, for surveying measurements, one is expected to identify these particular blunders that are mistakes by following standard methodology, eliminate that particular mistakes, then try to understand what are the errors, when they are occurring, why they are occurring, with what extent they are occurring. So this particular understanding will help us to take certain precautions, and hence will be able to reduce that particular errors as such. As we reduce these particular errors, still whatever that particular small fraction is remaining, for that the laws of the probability will be applied and the dimensions that we get, measurements that we get will be rectified and accordingly will be used for further plotting purposes. So we'll discuss about random errors. So this average of many measurements for the single entity under similar conditions is mean value. The way we discussed, we can have set of measurements for the given setup under similar conditions, and as we obtain average of that, it would be considered as the mean value of the entity under consideration. It is treated to be more reliable as compared to any single measurement, and hence it could be accepted as most probable value as such. One more term we have to use is residual. It is also called as variation, and it is a difference in measurement and mean value. Random errors account for misclosure when systematic errors have been corrected and blunders have been removed. Here, the way you see for this particular traversing was expected to start from A through B, C, D, E, F, G, and again coming back to A. But as the linear measures and angular measures are used to plot this particular traverse, the last station obtained is A dash and it is not coinciding with A. As such, this A dash is misclosure. A dash is due to misclosure and it has occurred because of the random errors which we could not observe, which we could not exactly identify, hence which we could not rectify during the process of this particular survey. So, the way I mentioned, these random errors conform to the laws of the probability and hence we can estimate these by making use of laws of probability. As we apply these particular laws of probability and these are occurring over the surveying processes, these are equally distributed through the entire surveying process. To understand their distribution, we can make use of normal distribution. It is also called as Gaussian distribution, or it is also called as bell-shaped distribution. These random errors or accidental errors follow this particular normal distribution. This normal distribution is the probability function that describes how the value of the variable are distributed. Mathematically, it is expressed as fx is equal to 1 upon sigma root 2 pi e raised to minus 1 pi nu by sigma bracket square. The terms that are involved here will be discussing shortly. So, it is symmetric distribution where most of the observation cluster around the central peak and the probabilities for the values further away from their mean taper off equally in both the direction. In order to understand the meaning related with this particular normal or this particular bell-shaped distribution, let's consider certain example as discussed on this particular block. So here, this particular distribution is expressed through this particular bell-shaped curve for certain set of observations that are nothing but heights which are typically measured for certain girls. So here these particular data. So as we see, most girls are close to the average of 1.512 meters. Here, the small differences between the individual's height and the mean occur more frequently than substantial deviation from their mean. So here, as you see on this particular either side, these particular small deviations here with respect to the average height of 1.512 meters, certain say 1.5 meters or 1.52 meters, the way you see here these particular differences are occurring more frequently, whereas the way you see here say certain extreme measures like 1.3 meter or this particular say 1.7 meter is occurring with that way remotely. Here the occurrence is much remote as far as their deviation with respect to the mean value is concerned. Here, as you see, the measurements could be expressed in form of the histogram. The actual measurements may be giving the set towards right. It could be giving towards left, or otherwise even the distribution could be certain jumbled as such. But for the given set of the measurements, we can have the residuals plotted against this particular say frequency in order to get this particular bell-shaped curve as such. So here their characteristics can be considered as listed down here. The small variations have more frequency than large ones. The way we considered in earlier figure also with respect to this particular say mean value. Here these particular small variations are occurring in number of times, whereas large variations are occurring that way with less frequency. As you see here, the deviation towards right and deviation towards left, so to say, positive and negative variations are having equal frequency. Hence, 50% of the values less than mean and 50% of the values which are greater than the mean, here the curve is described because of these particular values as symmetrical value. As we have this particular normal distribution, the area under this particular curve is expressed to be unity, that is 1, as well as for this mean, median, as well as the mode are equal. As we consider the narrowness of this particular spread, the values will be quite close to each other, hence there will be high precision. Whereas as we consider the large spread, the values will be spread on either side considerably, and hence this large spread indicates that the data is low precise. Here we can make use of standard deviation in order to understand the spread of these particular data with respect to the mean observation. Hence, the standard deviation is the measure of the variability, that is the indicator of reliability of set of these particular repeated measurements. So, the way we considered with respect to these particular say central value, If this particular graph is narrower, the spread will be lesser. As such, standard deviation will have small value, hence the data will be more precise. This standard deviation is determined by making use of this expression sigma. Sigma is nothing but the term that we use, symbol that we use for this particular standard deviation. So the sigma gives the standard deviation as square root of sigma nu square divided by n minus 1. Here, this nu is the residual, whereas n is nothing but number of measurements. Here, the 68% value, 95% value, 99.7% value are related with some specific cases of 1 standard deviation, 2 standard deviation and 3 standard deviation respectively. Let's assume that certain line AB has mean length of 3.3 meters and the standard deviation as determined by making use of this expression as 0.05 meters. So, as we make use of this particular say empirical rule, we can determine that 68% of the lengths are between 3.25 to 3.35 meters. As we determine 3.3 plus or minus 1 standard deviation. Whereas 95% are between 3.2 to 3.40 meter, which is determined as 30 plus or minus 2 times that standard deviation value. Similarly, 99.7% are between 3.15 and 3.45, which is determined as 30 plus or minus 3 times the standard deviation. The standard deviation, if squared, it gives variance. There are some other definitions related to standard deviation, and the surveyor needs to use that particular terminology. So here the most probable error is expressed as plus or minus 0.6745 times sigma. It gives the range for which there are 50% chances that the true value would lie in that range. So for example, if there is a 0.001 meter standard error for major value of the 1.1 meter, then there are 50% chances that the true value will lie between 1.1 plus 0.001 and 1.1 minus 0.001. Here, one more reference I would like to give in order to understand the most probable error, as well as the concepts of this particular standard deviation, which are more elaborated by Dr. Donald. So here you may please make use of this particular reference. Standard error is expressed as E68.3. It is nothing but the standard deviation. It establishes the limit within which the measurements are expected to fall 68.3% of the time, the way I have shown on the previous slide. One more terminology that you can use is standard or root mean square error of the mean. It is determined by sigma m is equal to plus or minus sigma by root n. It indicates the probability of the mean value lying between plus or minus sigma as 68.3%. Generally, E99.9 is taken as maximum error and it corresponds to range of plus or minus 3.29 sigma. So, for the given set of measurements, if any measurement deviates from the mean with plus or minus 3.29 times sigma, the measurement would be considered as mistake and it would be removed from the set of measurements. The most probable error of the mean is expressed as EM and it is nothing but 0.6745 sigma by root m. There is a necessity to express the precision of the various measurements. So, in order to express this particular precision of the various measurements, the term that we make use of is nothing but this relative precision. It is expressed as ratio of standard deviation to mean value of the measurements that we made. Here, usually it is expressed as 1 by m by sigma. It can also be used to show the confidence interval for measurement. So, for example, if this relative precision is 10% and the measurement is 22 meter, the confidence interval is 22 plus or minus 2.2 meters. Degree of accuracy is the specific term which is indicating the actual accuracy that is attained in the measurement. So here it is expressed as the ratio of the error and the measured quantity with the numerator as unit. So here, say for example, if we consider the linear measurements, it is the ratio of standard error to this particular measured distance. If we are working on the traverse, it will be ratio of error of closure to the total perimeter of the traverse. If we are dealing with angular measurements, one can make use of this particular expression k root n, where this k is nothing but the least count of angle measuring equipment, n is the number of angles that are measured. Similarly, here for leveling measurements, we can make use of certain standardized factor depending on the class of that particular leveling, and these particular factors will be used as the value of k under root L, whereas this L is the distance traversed by leveling equipment. As we proceed further with the various problems pertaining to set of measurements as well as methodologies that are adopted for various surveying operations, you will be more clear with the terms that we try to get introduced in this particular presentation. Lastly, we'll think of the order of accuracy. So here, this order of accuracy is the term associated with expected degree of accuracy. Say, for example, if we are dealing with certain horizontal distance measurement, and if the degree of accuracy expected is first order, we have to have the order of accuracy as 1 in 25,000. That is, here the major dimension, if is of 25,000 units, it may vary from its true nature by plus or minus 1 unit. Similarly, here in 10,000 units, we are allowed to commit plus or minus 1 error, provided we are dealing with this, say, second order of surveying, and accordingly here there will be third order classification. So thank you friends, thanks for your attention. We'll discuss more about now horizontal and vertical measurements as well as even the angular measurements in land surveying in our subsequent presentations. As we deal with horizontal measurement, vertical measurement as well as this particular angular measurement, whatever the concepts that we try to discuss may be For traversing triangulation, will be touching as and when required, and accordingly the concepts will be more clearer to you. So I wish you very happy learning. So bye till our next presentation. Thank you.